We are moving into Unit 5 for chemistry. Unit 5 is about light and how light interacts with the atom and then what we've learned from that. So we're going to return back to the model of the atom. The last time we left it, we had discovered that, or we knew how the protons, electrons, and neutrons had been discovered. So we knew there were subatomic particles in the atom. We knew that the protons and neutrons were in the nucleus. Now we're going to start focus on the electrons. And this unit, and then actually of many of the rest of the units, we're going to come back to the electrons, because it turns out that the electrons are what give the atoms their character. Why certain atoms act the way they do, why compounds act the way they do, always goes back to the electrons. So here we go. In this first set of notes, we are going to cover Learning Targets 5.1, identifying the relationship between wavelength and frequency, and also talking about what those two things are. Also differentiating the types of electromagnetic radiation and talking about what electromagnetic radiation is based on frequency and wavelength. And then students who are in Honors Chem, we're also going to do some calculations relating wavelength and frequency. We will bring energy into this as well, and Ms. Ehlert is going to work on that in the second set of notes. So let's start talking about light. So first of all, I want to talk about this term, electromagnetic radiation, or EMR. This is, if you break that down, so electricity, magnetic is, magnetism, and then radiation. So when we're talking about light and a few other different types of radiation, they all fit into this category called electromagnetic radiation because they all have similar properties and act a similar way. And they radiate, they're able to move through a vacuum. They don't actually need matter to move through, because if we think back to that discussion about matter, light is one of the things that is not matter. Light is energy, and this particular form of energy is known as electromagnetic radiation. So you've been dealing with light for a very long time, and you know it can come from the sun, which is a star, and now based on the previous unit, or one of the previous units, you should also know the process, the name of the process that does create that light, which is fusion. We're fusing atoms together, and by doing that, it creates a lot of energy. One form of that is going to be light. You can also know that you turn on a light bulb and you get light. So we can get light from a lot of different places. And you've probably also experienced some phenomenon that only occur with light. And this is, when we talk about light, light acts like a wave. And when you think about waves, probably the ocean is the most common thing that you can think about as waves. Water moves, and you can do it has certain properties, and that's what we're going to start talking about. So things you've seen, light passing through a prism. If you're a fan of Pink Floyd, this is the cover of one of Pink Floyd's albums, and you probably have experienced this many times. Same idea as when we have a rainbow. This picture was actually taken, you can actually see the football stadium right there. It was taken earlier this fall. And we commonly see rainbows after storms because raindrops or water in the atmosphere acts as the prism that splits the light up into its different parts. This is known as diffraction of light. We can split it up into different parts. You also may have experienced this phenomenon where you put a straw in water, and when you look at it at the surface level, you notice that the straw appears to be broken into two. That is a property of waves called refraction. And the last one is interference. And let me let you a chance to kind of write these down as to what different phenomenon are known as. And then interference, I want to get that one a little bit closer. So when you look at light, so we have a couple different stage lights here. Both of these are producing light, and when you look at where they come together, that's interference. So right here, this is a property only of waves. Particles do not do this. If I take two particles and I throw them at each other and they hit each other, they're just going to bounce off each other. They're not going to form into a bigger particle, which is what light is doing right here. You can see how it gets, the brightness is more when you have the two light sources together, and that's what we call interference. There's two different types. We have constructive interference, which is what this is, and then we have destructive interference, which is how sound canceling headphones work. So a sound is also a wave, and if you emit a wave of the exact opposite of the wave that you're trying to cancel out, they actually will cancel each other out and you can't hear anything. Same stealth technology also works like this. So these are all things that light can do that way we've always thought light is a wave. It has these properties of a wave. So let's talk a little bit more about waves. So there's two main properties of waves that we want you to know. One is known as the wavelength. The wavelength is the distance between two corresponding parts of a wave. So in this example, I chose this point right here, this point right here, and it's this distance between them that is known as the wavelength. It is not following up and down like a roller coaster, it's just going straight across. I also could have chosen this point, and that would have been a wavelength, and it would be the same. So that's how when we draw or think about a wave, that's how we model it, and that's how we would measure the wavelength. Wavelengths are usually measured in some sort of length unit when we're talking about light, and we will use nanometers. Nanometers is smaller, so we had millimeters was the smallest thing we talked about previously. A nanometer is much smaller than that. 1 meter is equal to 1 times 10 to the 9th nanometers. So it's good for everyone to know this. This number, students who are in honors chemistry, this is a number you definitely need to write down and start to memorize. All right, let's go to another property. So another property of waves are frequency. We can also measure the frequency of a wave. Frequency is the number of cycles that pass by a given point in 1 second. So in my GIF here, I'm using the line over here as the point, and we've got two different wavelengths. So what you're going to be doing to figure out the frequency is you would count how many times the top of the wave goes past that point. So this one's 1, 2, 3. All right, if I go down to the blue wave, if I go at the same, I'm looking at the top, I go 1, 2, 3, 4, 5, and you can already tell I'm saying my numbers more frequently. So that blue wave has a higher frequency. There's more cycles that pass by a given point. The unit we use to measure this is going to be per second, or second to the -1, because it's how many times per second. This also gives you a look at a different type of wavelength. So you can see how wavelengths can be different. So the red wave here has a longer wavelength. It's a longer distance between any 2 points. The blue wavelength has a shorter wavelength. All right. All right, electromagnetic radiation, again, like I said, also known as light. So here is a very busy diagram, and I want to give you a little bit of time to process this diagram. So I want you to take a look at it, and you will be provided with this diagram when you are taking tests. It's not something you need to memorize, but you do need to know how to use it. So I want you to take like a minute or so and look at different things and try to notice different things about it. Identify things that you see. So some of the things that you might be seeing are that we have different types of electromagnetic radiation. So we have this visible light, which is what I've been talking about. That's the one we are most familiar with. But we also have words we've seen before. And so we talked about gamma rays, or we talked about gamma decay, which forms gamma rays. X-rays, you're familiar with those, probably from the doctor or the dentist. Ultraviolet light, or UV light, you may have heard of that as well. If you have a black light at home, that is the type of light that emits, and then that bounces off of things and gives things kind of an eerie glow. Infrared light is what you might be familiar with the thermometers. Remember when we were at school and you came in during first hour and we pointed the thermometer at you, but we didn't have to touch you. We just clicked a button and we knew the temperature. That was measuring infrared radiation, because infrared radiation is what our bodies sense as heat. Microwave radiation. This is the same thing as the microwaves in your houses. So that is also electromagnetic radiation, and that heats up your food by causing the water particles or any or other types of particles to move around and vibrate, and then that creates heat. We also have radio frequencies. So I think you all still know what a radio is. I don't know, at some point people might not know what the radio is, but I'm kind of being funny, but kind of not. Okay, so that's one thing you might notice is we have different types of IR radiation. Also, and then within the visible, we have the different colors. So back to that rainbow or Roy G. Biv. So we have our red over here, orange, yellow, green, blue, violet. So you also might notice that we have wavelengths. So again, one property of light is that, or one characteristic is that we can measure the wavelength. And these wavelengths, like I said, are measured in nanometers, and they vary. From gamma rays have a very small wavelength, 10 to the negative 2, so tiny. Then radio frequency, 10 to the 12th nanometers, which is a little bit bigger. And if we do, I'm going to use that nanometer calculation that I just talked about. So let's figure out what that is in a number we know, we understand a little bit more. So if you take 10 to the 12th nanometers, and earlier I said that there's 10 to the 9th nanometers in 1 meter, this is going to be 10 to the 3rd nanometers, which is the same as 1 kilometer. So that is what radio waves, their frequency is about 1 kilometer. And you might notice that how the wavelength and the type of radiation start to impact each other or start to correlate to each other. So X-rays, gamma rays, these are things that we don't tend to want to be around for very long periods of time. They also have shorter wavelengths, so that, and also we think about ultraviolet or UV radiation, that might click in your head that, wait, that's what can give you sunburns and skin cancer. All right, so all things on this short wavelength, and these can be a little more damaging to the human body. Third thing, hopefully you noticed, is that we have different frequencies. And again, I mentioned that frequency is 10 per second, and this is how we tend to write it, second to the negative 1. And the frequencies here is 10 to the 4th. So this is the small end for the frequencies, and they increase as they head over to that end. So let's get a few questions in of things that we want you to be able to relate on this slide. All right, so one thing that we want you to be able to know is what's the relationship between wavelength and frequency. So this goes back to when we were talking about dependent and independent variables, not exactly the same way, but when we ask for a relationship, we want a statement like this. So when the wavelength does something, the frequency does something else. So as we see for the wavelengths, you can see the arrow here, as the wavelengths increase, I'm going to start with that one, the frequency is going the other direction, so the frequency decreases. And this also fits with what you were just seeing with that GIF earlier. The red had a longer wavelength that had a longer wavelength, and it had a shorter frequency, lower frequency. The wavelength that was really short had a higher frequency. All right, let's go on to another one. All right, so what type of wavelength or what type of EMR? So the types of EMR are right here in the center. This is what we're looking for an answer when we ask for type of EMR. Has a wavelength of 5.4 times 10 to the 6th nanometers. I'm going to give you a short time to try to figure that out, and then I'll go through it. All right, so a couple things you want to identify. You need to identify which the characteristics we're looking at. We want wavelength. Wavelength is up here. And the number we want is, first of all, in nanometers, and that's what we have, so we don't need to do any conversions. And we've got 5.4 times 10 to the 6th. So 10 to the 6th is right here. So the answer to this one would be a microwave. Has a wavelength of 5.4 times 10 to the 6th. Try another one. What type of EMR has a wavelength of 500 nanometers? Again, I'll give you a short time to try to process it and figure it out on your own. All right, so with this one, hopefully you are noticing that, hey, 500 nanometers is right here. So there'd be two possible answers for this one. Probably the best answer would be green visible light. But visible light is really what we're going for, but this particular wavelength happens to be in what we would call green light. All right, next one. What type of EMR has a frequency of 5.0 times 10 to the 18th per second? So again, I'm gonna give you a short time to try to figure it out on your own. All right, so again, keywords here. Frequency is a keyword, and so I know I'm looking at this scale, 10 to the 18th. So I scan down here and I find 10 to the 18th, and it looks like the type of EMR that has that frequency is the X-ray. You may have noticed when you ever have X-rays, there's a couple things that the X-ray technicians will do. One, they will not be in the room. Two, they will cover you with a lead shield. And the reason they do that, again, is because X-rays, if they get into your body, they can cause damage. And so it's all about risk management. Like, we know the benefit of having an X-ray, but we also want to make sure that we're taking as many precautions as we can to be able to get that benefit and not have a detrimental effect on ourselves. That's why the technician leaves the room, is because they're around these things all the time. And if they stayed in the room, they would be exposed to way too much radiation. All right, let's go with the last question on this set. So what type of EMR has a frequency of 4.5 times 10 to the 13th per seconds? Or seconds to the -1. It's kind of an awkward thing to say. All right, so again, frequency is our key word here. So we're looking at this part of the diagram, and we want 10 to the 13th. And so 10 to the 13th is going to be between 10 to the 14th and 10 to the 12th. So this type of EMR is infrared radiation. Or you could also write IR or infrared. All right, so to kind of summarize this, here's some of the relationships that we want you to know. That wavelength is inversely related to frequency. Now, inversely is not a term we've talked about before in this class. Inversely means as one increases, the other decreases. We're going to see this whenever we're relating variables. One will have an impact on the other one, but in this case, the impact is an inverse relationship. So the formula that we want you to know, again, students in Honors Chem, you're going to be doing calculations with this, but we want everyone to know this, is C is equal to wavelength times frequency. And we've got some new notations in here. Frequency is going to be that fancy looking V, or also known as a nu. And the wavelength is lambda. That's the name of that letter. And wavelength is in meters. So most of the wavelengths we just worked with were in nanometers. And so being able to convert between meters and nanometers is going to be a skill that you're going to be practicing. All right, this C is something I just kind of threw in, but you've probably heard of the idea of this C before in this very famous equation, E equals mc squared. C stands for the speed of light, because all EMR travels at the same speed, very, very fast, the fastest speed we have, and that is the speed of light. So that speed of light, 3.00 times 10 to the 8th meters per second. All right, so for chemistry, that wraps us up for Honors Chem. We are going to keep going. All right, students who are in Honors Chem, let's keep going with some calculations. So this is the equation that we're going to be using. C is equal to the wavelength times the frequency. And it is important to pay attention, as it always is, to the units, but this one particularly because Usually when we're reporting wavelength, we report it in or measure it in nanometers. However, in order to use this equation, you need to have it in meters. The reason you do that is because the speed of light, the constant that we're using, is in meters per second. So that's the only way that the units are going to work out to make things calculate correctly. All right, let's try this first example. Calculate the wavelength in nanometers. Because remember, when we use this equation, C is wavelength times frequency, the answer we're going to get for the wavelength is going to be in meters. So we're going to have a two-part solution here. Of EMR that has a frequency of 6.54 times 10 to the 17th seconds to the -1. So it is fairly straightforward, except for the conversion between the meters and the nanometers. So I just start plugging my numbers in. C is 3.00 times 10 to the 8th meters per second. And that is equal to the frequency, the wavelength, times the frequency, which is 6.54 times 10 to the 17th seconds to the -1. When you plug that into your calculator, you should get 4.59 times 10 to the -10 meters. So verify that you're able to enter in using scientific notation, because again, that's the challenging part sometimes. So that's in meters, but remember, we wanted the answer in nanometers, so I have to go one step further, and I take that answer, and just simply using dimensional analysis, I can convert it. So I know that 1 meter is 10 to the 9th nanometers. So I'm going to be able to plug that in. So put that into your calculator. And I end up with an answer of 0.459 nanometers is going to be my wavelength. And then we also want you to be familiar with the type of wavelength. So I'm going to take that number and I'm going to go back to the slide that had all of the information for the wavelengths. Come on. There we go. Okay, so I'm looking for, I can look for either. I could look for the frequency or I could look for the wavelength. They're going to give you the same answer. So if I'm looking for this wavelength, I'm going to find it over here in the X-ray, as well as if I look for the frequency, 10 to the 17th, that would also be X-ray. So the type of EMR I have in this case is X-ray. For calculation number 2, if you feel like you're confident with this and you just want to try it, go ahead and pause the video and then try it. If not, then I will start walking through it. All right, so now we need to find the frequency. What's the frequency, Kenneth? If you know REM, that's an old REM song, of EMR that has a wavelength of 650 nanometers. So the equation I'm going to want to use is the one that relates the wavelength and the frequency, which again is C is equal to the wavelength times the frequency. So I'm going to start putting my constant in, so 3.00 times 10 to the 8th meters per second. All right, and then right away I write meters here and I start looking at that wavelength unit and it's not the same. So I need to make sure I remember to convert that nanometers into meters. So I have 650 exactly meters. The relationship between meter and nanometer it's kind of easy to remember because nano is 9 and nano is, just have to know that it's really small. So 10 to the 9th nanometers is equivalent to 1 meter. So go ahead and put that into your calculator. All right, and you should be getting 6.50 times 10 to the -7 meters. So nanometers cancel out. The other way you could look at this, if scientific notation is something that you feel like you get pretty well, really what I'm doing is taking 6.5 times 10 to the 2nd divided by 10 to the 9th. So it's really 2 minus 7, 2 minus 9 is where I get that -7. So if that makes sense to you, you can use that to do some of these conversions pretty quickly. If it doesn't, just let it go keep working with this conversion. So now I have my wavelength, 6.50 times 10 to the negative 7 meters times the frequency. So then I, again, plug it into the calculator. So go ahead and do that. A lot of work with the scientific notation entering in. So when I get that frequency, 4.62 times 10 to the 14, you can either write per seconds or second to the negative 1. Both of those would mean the same thing. If you just look quickly here at the units, you can see how everything works out. I know I need meters per second, and I am taking meters, and I have to multiply it by 1 over seconds. So mathematically, that's how the units work out. But again, the definition of frequency is how many waves go by a certain point in a second. So it would make sense that it's a number per second. All right, so now that I have those numbers, I can use the diagram that we'd given you before to figure out what type of EMR this is. So this time I put it on the very next slide. So the two things I'm looking for, again, you can look for either. You can look for the nanometers, or you could look for the frequency. We just want you getting used to it. So if I have a nanometers of 650, let's just make this really, okay, I have a nanometers of 650. That fits down here. So I've got this red-orange visible light. But again, really what we're going for is visible light. If you give us the color, bonus, but it's not necessary. All right, and those are the type of calculations you're going to need to be able to do for this section.